Hello everyone. Welcome back to physics. Let me begin with a little thought experiment. Have you ever stared at a cut glass chandelier or played with a prism in the lab? The way they bend sunlight and sometimes even split it into rainbow colors, it feels like magic, doesn't it? But nope, it's not magic, it's pure refraction at work. Now here's something really cool. A lens, which is just another piece of glass or transparent plastic, can actually be imagined as a collection of many tiny prisms, all neatly arranged side by side. Each tiny prism bends light just a little. But when you put hundreds of them together, the effect adds up. Suddenly, the whole lens starts controlling light rays in a very systematic way. Here's the fun part. When all those tiny prisms bend rays inward, the lens as a whole makes the rays meet at a single point. That's a convex lens, the converger. On the other hand, if all those prisms push rays outward, the lens spreads them apart and we get a concave lens, the diverger. It's almost like teamwork. One prism can't do much on its own, but when the whole family joins forces, they decide the fate of the light ray, either a friendly group hug at a focus or a dramatic scatter in all directions. So next time you hold a magnifying glass or even wear your spectacles, just imagine, inside that lens are countless invisible prisms quietly working together to bend light exactly where you need it. Alright class, let's zoom in on how a convex lens actually does its magic. Here's a simple way to think of it. A convex lens is really just a clever set of tiny prisms stacked side by side. Each prism bends incoming rays just a little bit, but together they make the rays bend toward the principal axis. Now watch what happens when parallel rays enter this lens. Instead of continuing straight, they all bend inwards and finally meet at a single point called the principal focus. That's the power of a converging lens. It takes wandering rays and organizes them into a perfect meeting spot. Notice something interesting. The bending isn't the same everywhere. At the edges of the lens, rays bend much more sharply compared to the rays near the center. And it's this stronger bending at the edges that gives the convex lens its excellent focusing power. You can test this with a magnifying glass, move it just right under sunlight, and you'll see all the rays concentrating into one bright spot hot enough to burn paper. Yes, science at work. So to recap, a convex lens behaves like a team of prisms pulling light rays together, with the edges doing the heavy lifting. And that's why we call it a converging lens. Alright class, we just saw how a convex lens acts like a team of prisms pulling rays together. Now let's meet its opposite cousin, the concave lens, which does the exact reverse. In a concave lens, the prisms are arranged the other way around. So instead of bending rays toward the principal axis, they bend them away from it. It's like the opposite of a group hug, more like everyone politely stepping back and saying, "You go your way, I'll go mine." Now here's the clever part. When parallel rays enter a concave lens, they don't actually meet at all. Instead, they appear to diverge from a point behind the lens. We call that point the virtual focus. Think of it like a magician's trick. The rays look as if they're starting from behind the lens, even though they never really did. And this property makes concave lenses very useful in real life. For example, they are used in spectacles to correct short-sightedness. Without them, distant objects look blurry, but the concave lens spreads the light just right so that your eyes can bring it back into focus. In other words, if you've ever seen a classmate squinting at the board but reading their phone perfectly, thank the concave lens for coming to their rescue. So to recap, convex lenses gather, concave lenses scatter, and both, in their own way, help us see the world clearly. Now here's an interesting question. Why do rays bend more at the edges of a lens than at the center? The prism model gives us a very neat explanation. At the edges of the lens, the prisms are tilted at a greater angle. More tilt means stronger refraction, the rays get bent more sharply. It's like riding a bike on a steep curve. The sharper the curve, the harder you have to turn. At the center of the lens, the prisms are almost rectangular, almost like little glass bricks. Because they hardly tilt, rays passing through the middle barely bend at all. They just stroll straight through, cool and relaxed, without much drama. This difference in bending is what ensures the magic of lenses. In a convex lens, the stronger bending at the edges makes rays converge to a single focus. In a concave lens, the same idea causes rays to spread apart. So the very same principle works in opposite ways depending on the lens shape. And here's the cherry on top. This prism model also explains why rays passing through the optical center of a lens travel straight without deviation. Because right there, the prism surfaces are balanced, no net bending. It's like walking through a doorway without anyone pushing from either side. So, to sum up, edges bend more because prisms there are steep, the center bends less because prisms are flat, and together, they make lenses the powerful light benders that they are. Now let's connect prisms and lenses with a little bit of math magic. In a prism, the deviation angle, that is how much a ray bends, depends on two things, the prism angle and the refractive index of the material. We have a simple formula for this, delta equals mu minus 1 multiplied by A. Here delta stands for the deviation angle, mu is the refractive index, and A is the prism angle. In everyday words, the larger the prism angle or the higher the refractive index, the more strongly the prism bends the light. Think of it like turning a steering wheel, the sharper the angle, the more the car swerves. Now, since a lens is basically a collection of many prisms put together, the overall bending of rays in a lens also follows this rule. Each tiny prism adds its own little deviation, and together they decide how the whole lens acts. Here's the key idea. If a lens has greater curvature, then the prisms near its edges are steeper. Steeper prisms mean stronger bending of light. That's why a lens with greater curvature ends up with a shorter focal length. It pulls the rays in more strongly. So whenever you see a thick magnifying glass at work, remember, it's just a powerful team of little prisms, each bending light according to delta equals mu minus 1 times A. Okay class, let's work through an example to really see how the prism model explains convergence in a convex lens. Step 1. We take a convex lens with a focal length of 10 centimeters. Imagine a ray of light entering near the edge of the lens. At the edge, the prism angle A is small, and for simplicity we assume it to be about 10 degrees. Step 2. Now recall the prism formula, delta equals mu minus 1 multiplied by A. Here, delta is the deviation angle, mu is the refractive index, and A is the prism angle.
Step 4. What does this mean physically? This 5-degree deviation at the edge is what helps bend those parallel rays inwards, steering them toward the focus of the convex lens, which is at 10 centimeters from the optical center. Step 5. And there's our conclusion. The prism model beautifully justifies how a convex lens makes parallel rays converge at its focus. It's like each tiny prism is a traffic officer giving rays a gentle nudge, and together they guide all the rays into a single meeting point. So, the math works out, the physics works out, and the prism story makes lens action easy to understand.
Alright students, let's wrap up this whole idea of lenses as prisms with a neat little recap. Think of this as putting all the puzzle pieces back in the box. First, a lens can be modeled as a collection of many tiny prisms, all arranged side by side. Each one bends light just a little, and together they decide whether rays meet or scatter. It's teamwork at its finest. Now here's the big difference. Prisms in a convex lens bend rays inward, pulling them toward the principal axis. That's why convex lenses are converging. In a concave lens, the prisms bend rays outward, making them spread apart. So convex is the gatherer, concave is the scatterer, easy to remember. Next, recall that bending isn't uniform. It's stronger at the edges because prisms there are angled more steeply, and it's negligible at the optical center because those prisms are nearly flat. That's also why rays through the optical center go straight, undeviated. Finally, here's a formula reminder: delta equals mu minus 1 multiplied by A. Delta is the deviation, mu is the refractive index, and A is the prism angle. This simple relation links prism deviation directly to how lenses behave. So, to put it all together, lenses act as coordinated armies of tiny prisms, the edges doing the heavy bending, the center staying calm, and the whole lens shaping light exactly the way we need. From your spectacles to cameras to microscopes, this is the prism model quietly at work behind the scenes.